Hello. Okay. You should see the desktop by now. And do you hear my voice? Does everything seem okay?
Yep.
Okay. Let me get this. Okay. All right. We're gonna keep talking about finish these two renders here. Remember there's a homework assignment due today. If you have questions about it, just send me emails and okay. And there is this take-home exam a week from today. Okay, so if you have questions about the review problems, let me know. And the exam includes up to this renderer 5. So it has a few questions about renderer 5. So we're going to talk about renderer 5. Now, renderer 4, I think we finished talking about anti-aliasing. Okay. Now, I mentioned anti-aliasing is another application of LERP, and LERP is really important. Anti-aliasing is interesting, but it's becoming less interesting as time goes on because monitors are getting so uh, the pixels on monitors are getting so tiny that you don't see the jagged lines anymore. Like 10 years ago, 15 years ago, they were pretty noticeable. The pixels were way bigger than they are now. Uh, I don't have a machine with a 4K monitor or a Retina display. I think with those, it's almost gotten to the point where anti-aliasing isn't needed. I'm not really positive because I don't have one, and I haven't really seen it much talk about that in literature. But I know my desktop is not that high a resolution. It's higher than monitors 10 years ago. I'm using a laptop here, but it's still nowhere near as high resolution as a Retina. So, for example, uh, my laptop is doing 125%. This kind of gives you a sense of how big your pixels are. On a Retina display, this would be 200%. Yeah, on a Retina display, they magnify by two. Okay, so 125% means my pixels are a little bit smaller than what they used to be some years ago. So it's magnifying a little bit because most old programs don't know about tiny pixels. So this is a huge problem these days. Most programs were written before there were tiny pixels. So when a program says a button is 100 pixels across, that's when you get these buttons that are so small. Sometimes you run a program and everything's so tiny you can hardly click on it. It's because it's not being magnified, and the program said buttons are 100 pixels wide, but now 100 pixels isn't what 100 pixels used to be. So the Windows tries to automatically magnify your programs, but not all of them obey the Windows magnification. It's kind of a mess. Okay, some programs have, for some reason, some of them either disable the magnification from Windows or they don't somehow work well with it, and you get weird effects. But Windows is trying to magnify everything. So if I turn it off, see everything shrinks. Now this isn't too bad. I could probably get away with this. You know, I could probably use this. Some people may have no trouble with it, but that's not really what it's really supposed to look like. I mean, even Chrome probably doesn't expect the fonts to be that small. Chrome is probably expecting the fonts to be about what they are when I magnify it, because Chrome has trouble with the fact that some of your desktops have big pixels, some of your desktops have medium-sized pixels, and some of your desktops have teeny pixels. So even for, it's a nuisance. It's hard to deal with this. In a few more years, all the monitors will have small pixels, and maybe at some point this scaling will go away. Okay. Notice that they give you a warning. Some apps won't respond to scaling changes until you close them. Yeah, and there's some programs that don't respond to scaling very well at all. Okay, I'll put it back where it's recommended. Okay, so anti-aliasing is not, it's interesting, and it's been a huge part of the computer graphics world for years and years and years since the beginning, but I bet it's going to fade away. I wouldn't be surprised if less and less is said about anti-aliasing because monitors get more higher and higher resolution. Okay, now we also want to start adding color to our render. So let me show you what it looks like now. Here's what we have. Okay, the render is not now going to be able to display in color. If you hit the C key, it'll change the color, and everything's in color now, and you can change the color. Okay, that's interesting. And now, if I go back, remember this. Go think of this model here. Whoops. Okay, that's a square. So a square is 1, 2, 3, 4 vertices and 4 line segments. And if I turn on debugging, we can see that that square, the square is 4 vertices. Okay, 1, 2, 3, 4. Now it's also got 4 line segments. There's line segment from that vertex to that vertex, that vertex to vertex. Okay, so it's 4 line segments and 4 vertices. Now it also includes, now what the renderer does is that line segment, see there's 4 vertices. Okay, vertex 0 is shared by 2 line segments. So this line segment would have a reference to that vertex, and this line segment would have a reference to that vertex. Similarly, this vertex is shared by those 2 line segments. So this line segment and this line segment both point to that vertex. So there's 4 so there could have been 8 vertices in this. I mean, sometimes we want to have 2 vertices here, one for this line segment and one for this line segment. If we wanted this to be something that would open up, for example, if we wanted this square to open up, we would need 2 vertices over here so that this thing could swing open. And right now, with just 1 vertex there, if you move that point, both line segments move together. So if you move that vertex, 2 line segments move. What if you wanted to move that vertex, not that one? So right now, there's those 2 line segments share that vertex. What we also have is now colors. For each line segment, there's now a color at that end and a color at that end. Okay, so right now I'm not actually painting in a bunch of colors, and we can see that if I change the one of the keys, see that key there. Okay. Notice how the line set, it changed quite a bit in color. Okay, this one's now keep changing the colors. Okay. Now here's interesting. Here shows you what's really going on. Look at this line segment. That line segment shifts from green to blue. Then this line segment shifts from light blue to violet. Okay, this line segment down here, well, it's kind of hard to see what those colors are at the end. But notice that the line segment shifting in color as you go across. What the render is doing is this vertex now has 2 colors associated with it. This line segment has 1 color at that vertex, and this line segment has a different color at that vertex. Remember a minute ago I said these 2 line segments could have different vertices at that point, but they share a vertex. Right now, they're not sharing. If I go like this, they share that color. So there's actually just 1 color at that vertex. And these 2 line segments, just like the vertex itself is shared by the 2 line segments, the color is shared by the 2 line segments. But if I do this, now, let's see, now that one didn't show up so well. The colors are just being generated randomly. So if I kind of keep going, I get a good choice of random colors there. This one's obviously yellow. This vertex is yellow at that line segment, but it's kind of reddish at this line segment. Okay, this vertex over here is green in that line segment, and it's blue. That vertex has got a blue color for this line segment. Then this color shifting that you see like here from red to purple, that's done by the linear interpolation. We'll see that the renderer is taking what color is at that vertex and what color is at that vertex and interpolating it across the line segment. Okay, so what we're going to do now is we're going to go through the details of how we give each line segment 2 vertex objects and 2 color objects. 1 vertex and 1 color for that end, 1 vertex and 1 color for that end. But the vertices and the colors can be shared, as we'll see in a minute, And so you can create different kinds of geometries and different kinds of color combinations. And if you go through, whoops, oh, let me turn off debugging. There's too much output from some of the complicated models just have way too much output. I'll just kill it and start it over again. The debugging output's real useful for small models, and for large models, unless you really need to debug something, the output's way too much. Okay. Um, see, I can just change the solid color of this, but I can also change the colors at all the vertices. Okay, and I can do it a couple different ways. Okay. So you notice it's multicolored here one way. It's actually multicolored here in a different way. We'll see in a minute what's slightly different about these. These are all slightly different ways of changing the color. Okay, and like here, there's a bunch of line segments, and you can change the color of all of them, or you can change them to see. Now it's kind of this. Each line segment has its own color. So that line segment has a different color than that, but it's a solid color across the line segment. And now each vertex now has two colors. One color for the line segment on its left and one color for the line segment on its right, and each line segment's being interpolated across. So each vertex has got two colors, one for the left and one for the right, and each line segment has got a rainbow of colors going across. Okay. And when you have like interesting models like this, you can change the color of them, or you could get these kind of rainbow effects where it's just here's just shifting, it's just randomly choosing colors over and over and over again. Okay, it looks kind of nicer if you zoom in on it. If you zoom in, you can see how the line segments have their own colors. You can see that the line segments have their own, and if you look at a vertex, emanating out of that vertex now is lots of different colors. That vertex has got a color on for a different color for each one of the line segments coming out of it. Let's see. Let me find one that's a little bit different. Oh, I can't remember. There. The way it works now is that vertex has a color, and all the line segments coming out of it have the same color. So there's one color for that vertex. So every line segment at that point has the same color. So there's one color at that vertex, and all the line segments coming into it share that color at that. Now they may have a different color at the other end of the line segment. So they all have that color when they reach that point in the line segment, but they may have a different color at the far ends. So they all start out yellow, and then they go out to another color. But like here, these two line segments have the same color coming in. Okay, so there's a bunch of different ways you can assign colors to vertices and line segments, and that's what we want to talk about next. So how does this actually get done? Okay, all right. So now I've made some changes to the way that the documentation works. In every renderer, there's a README file. And the way it works now is the README tells you what's new in that render. So this explains the anti-aliasing in the render. So it explains anti-aliasing. And this README explains colors in the render. Okay. And renderer 3 explains clipping. But then in each render folder, there's this overview page that's part of the Java doc. Okay. So each render has an overview page that's part of the Java doc. And if you build the Java doc, you can read that page. And what I tried to do is include all the READMEs. Essentially, it's a union of all the READMEs. So I'm trying to make that document be a document that describes the entire renderer. So if you build the Java doc and then go to the index file is that overview file. Java doc's kind of a weird way of doing it. So when you in the in the renderer, this overview file, when you generate the Java doc, becomes the index file. Okay. Okay. And it's not this overview file down here. See if you click, yeah, well, it's, well, the index file is the place where you're supposed to, it is, I think it is actually this, yeah, so this one and this one actually are the same. Normally, you're supposed to open it at the index. You're supposed to enter at the index, but it seems that the overview summary is a copy of the index. So, yeah. So if I double click on, let's see, yeah, if I click on that one, it does seem to open at the same place. Okay, but so does the index. See, they all say, oh, notice how they're all called overview at the top. So if I click on index, it takes me to the overview. Okay, so usually you're told that the entry point to the Java doc is the index, but the index actually is that overview. Okay, now I've made it so that this is a description of all the things about the render. So I kind of try to, this becomes essentially, hopefully, like the textbook, that this would be describing everything we've talked about so far. So I've tried to keep this thing pretty well up to date, that this describes all the ideas we've talked about. So it's kind of long because it's everything we've talked about. So there's the anti-aliasing. We skipped talking about the gamma correction. If you want to read about that, again, this stuff is becoming less important. But if you're interested in reading about that, you can read about the gamma correction. Okay, but here's what we're talking about today is color interpolation. Okay, so this thing includes everything now. So it's hard to say which is a better way to read it. If you start with renderer 1 and you read each README, you can see how the renderer progresses. But if you just open renderer 5 and read this overview, it describes everything about the render. Okay, and it just as new things are added to a render, they're folded into this document. Like this is what we want to talk about today: vertex, color, and allocating line segments. Okay. All right, so there's two ways. So there's two ways of reading the documentation. You could either start at renderer 1 and read the README for each render, or you could just, like, if you want to, from the point of view of what's on the exam, it's everything that's in this overview here for renderer 5. The overview for renderer 5 is pretty much everything we've talked about so far. Okay, now how are we going to do colors? What's the detail now for doing colors? Okay. If we look at the tree, here's the scene data structure. Here's where the change is made. A scene is a camera and a list of models. Okay, and a list of models, there's model 1, model 2, model 2. A model is a list of vertices. It's now a list of colors and a list of line segments. So the biggest changes here in model. A model is now a list of vertices, a list of color, and a list of line segments. Okay, now vertices haven't changed. A color, a color is an RGB. So say a vertex is an XYZ. I didn't have room to put it in here, but each color object is an RGB. Now, here's the other big change. A line segment has two indices in it that point to vertices, but now it's got two other indices that point to colors. So every line segment says, here's where my first vertex is, and here's where my second vertex is. And every line segment also says, here's the color to use on my first vertex, and here's the color to use on my second vertex. And the colors are indexes into the list of colors. Now we do it this way for the same reason we did the vertices this way. If we go back to that example, that square we did, the square pretty much gives you a sense of why we're doing it this way. Okay, if you think about a square, what we don't do is somehow have a bunch of points going across here. We're not going to model objects with a dense number of points, which like a painter paints across here. We're going to just say that what the model this model is really 4 corners. If I tell you that corner, that corner, that corner, and that corner, that's enough. Okay. Now, but what's at that corner is two line segments. I could have two vertices at that corner, one for that line segment or one for that line segment, or I could have one vertex at that corner and share them. So I want to have a versatile, I want the render to be versatile enough to be able to say, I want only one vertex there. So if I move that vertex, both line segments move with it. On the other hand, I want to be able to say that this line segment and this line segment are kind of independent of each other. I can grab that line segment and move it without moving that line segment there. So then I need two vertices there. So I really want a versatile structure that would let me say these two line segments are joined at that vertex versus these two line segments currently meet at that vertex, but this line segment can be pulled away. So that would mean that, I mean, in one case, I want the two line segments to share a single vertex so that when that vertex moves, both line segments move. On the other hand, I might want there to be two vertices there so that this guy can move without that guy's vertex being pulled away with it. Okay, so I want a structure that looks like that we said here, where the line segments, well, the vertices are in their own data structure. You have a list of vertices, and then a line segment can say which vertex it's using. Okay, so in this model, I could put two copies of that vertex in the vertex list. And then I could have one line segment point to one copy and one line segment point to the other copy, and then each one can move independent of the other. Or I could put one vertex for this guy in that vertex list, and then have each line segment share that vertex. Then if I move that vertex, both line segments move with it. So then the box stays, connected, but or for example, if I grab that line segment and pull it, it'll pull that line segment with it. And the same thing over here. I may want to pull that line. If I move that line segment, I may want that line segment to pull with it. For example, if I pull this up, maybe I want these to stretch. Or if I pull this up, maybe I want it to be a lid and it comes off. So I have different scenarios to model. Do I click on this line segment and drag it up and it disconnects? Or do I click on this line segment and drag it up and these two line segments stretch with it? And I model that by how I control how the line segments share vertices. Now we want to do the same thing with colors. We want to have this idea that at this vertex, like right now, there's just one color. So really what I would do here is I would put one color in the color list. And then see now this line segment, these two tell this line segment what vertices to use. This two indices point into the color list. So I could have this line segment, both of its color indices point to one color in the vertex list. Then that line segment's a solid color. Then I could have this other line segment, its color indices could point to the same single color. So I would have just one color object, and I would have this line segment point to that color object at each end, this line segment point to that same color object at each end. Okay. But what if I wanted so that I could possibly change the color of this line segment, but leave these the same? Well, then I would have to have more color objects in the color list and have the line segments point to different ones. For example, I may want, let me show you a different example. I colored this one in kind of here's how it's colored. The top is green, the bottom is red, and the vertical lines are blue. But it's really more than that. What I really did is I said the top edges all share one color. The bottom edges all share one color, and the vertical edges all share one color. So this model's got three colors. And if I use the C key, the Shift C key, it'll tell it to randomly change those three colors. But notice how it's randomly changing those three colors, but it's always staying. Get a good choice of random colors. Notice that the bottom is still all one color, the top is all one color, and the sides are a different color. So that's the Shift C key. It says what it does is it goes over here and it randomly changes the colors in here, but it doesn't change any of the indices over here. So the colors over here are being randomly replaced, But since the indices aren't being changed here, the model uses the colors in the same way. So this model is using 3 colors, 1 color from the bottom, 1 color for the top. Now I can see 1 color for the top, 1 color for the bottom, and 3 colors and 1 color for the vertical edges. Okay. So now to do that, that means that this vertex, see this corner needs more than 1 vertex. There can't be, well, I'm sorry, no, this corner has really just 1 vertex, but this line segment, when at that vertex, it'll point. So all the line segments share that 1 vertex. So this is a really connected cube. So there's just 1 vertex. So all the line segments will share 1 vertex. But this line segment will point to 1 color at that vertex, and this line segment will point to a different color at that vertex. Okay. Same like over here. Okay. At that vertex, there's only 1 vertex. So all the line segments, all 3 line segments share that same vertex. But that line segment has 1 color at that end, and those 2 line segments have a different color at their ends. Okay. Now, like here, this vertex and this line segment and that line segment use the same color object at that end, his left end and his back end, but this line segment uses a different color there. Okay. So I've got essentially a structure to the color. I don't have much structure here for the vertices. Like this box couldn't have the top lift off. Even though the top is color blue, the top can't lift off. If you try to move the top, all these edges will move with it. Because right now this thing is, if I turn on debugging, we can kind of see the structure of it in the debugger. Okay, so the model's got 1, 2, 3, 4, 5, 6, 7, 8 vertices. It's got exactly 8 vertices. Okay, so every one of these line segments is using the same vertex for that corner. Okay. Now it's only got, see, there's the 3 color objects. See, it's only got 3 color objects. Right now it's got a blue one for the top. It's got green for the middle, and yellowish. Oh no, I'm sorry. This is the model as it starts. Let me see. Yeah, this was the color as it started. So this is the model at the beginning. Now this is the model as it's being rendered. Now see, it's got different colors now. So it started with a red, green, blue, 3 colors. So this is what it started, but I changed them over here. So now, so it started out as 8 vertices, 3 colors, and 12 line segments. And you can see how it's laid out. One edge goes from vertex 0 to vertex 1. So one edge goes from here to here. So vertex 0 is 0, 0. That's this one. And that's in the back. See, it's at -2. So that's this vertex down here. Okay. And then there's another vertex at 1, 0. So that's this vertex over here. X1, Y0 in the back. Okay. So the first line segment is that one back there. Okay. Now it uses color 0, 0. Okay. That was red. See, at the beginning, it was red. Okay. In fact, actually, let's start it. Let's go back to beginning so we can see it. So what's up there agrees with the. Okay. Okay. So here's how the model's laid out in memory. So this essentially is a picture of how the model's laid out in memory. It's got 6 vertices, 3 colors, 12 line segments. Okay. The first line segment uses vertex 0 and 1. Go over here, vertex 0 is 0, 0. That's this guy down here, okay? And he's in the back, so -2 is farther away from us, okay? Line segment, the first line segment uses vertex 1, which is 1, 0. So that's x equals 1, y equals 0 in the back. So that's this edge here, okay? And that vertex, that edge uses the same color for both ends. It uses red at both ends. Then the next line segment uses vertexes 1 and 2. So it starts there, and it's going to go over to here, because vertex 2 is 1, vertex 0 is 1, 0, -1. See, it moves to the front. See, this one is in the back. This is the one in front of it. So you move from the back to the front. So that's the second edge. The second edge goes from that vertex to that vertex, and the second edge uses, again, color 0. And then the third and fourth edges, they use the same color at both ends. So all these line segments are using the same color at the both ends. They share the vertices. So these two line segments share that vertex, and they share the same color all the way around. Okay. And then you can see that the next 4 line segments are going to be the top 4. They're going to be this top 4. They all use vertex color 1. So there's color 1. Okay. Color 1 is the green. It's got the green. Okay. And then there's going to be the 4 line segments that go up and down. That's these last 4 line segments. They use color 2, which is blue. Okay. And see, like this line segment goes from vertex 0 to vertex 4. It goes from vertex 0 to vertex 4. That would be going from this vertex to that vertex. So you can go through and read this and check. That goes from this vertex. This is vertex 0. This is 0, 1, 2, 3. And this is vertex 4, 5, 6, 7. So you go from 0 to 4. Then you go from 1 to 5. So from 1 to 5, and so all the vertical edges use color blue. Okay. Now, if I change the color, I'll change the color, and then I'll debug it, turn on the debugging. Okay. Now I can see that now I haven't changed, the vertices haven't changed. Okay. Now here, the lines didn't get clipped. So it tells you here what the line, now here the clipper is telling you what the line segments look like. So the first line segment is from vertex 0 to vertex 1 using color 0. But color 0 now is this color here. That's this funny kind of color down here that we see at the bottom. It's the color 212911105. So they're just randomly generating color. But you can see that the first line segment and the second line segment and the third line segment and the fourth line segment are still all using color 0. See, they're using the color index 0. So those line segments are all using, all these line segments down here are using the same color. Okay, and then you can go through the next 4 line segments will be, let's see, that was 1, 2, 3, 4. So here's the beginning of the next 4 line segments. So the next 4 line segments, did I do that right? Did I count that right? Oh, I'm sorry. Here's a line segment. You're told that it's trivially accepted, so then it's repeated. Okay, so the line segment, because if the line segment had been clipped, here you would get the new clipped line segment. So the debugging output says, here's the line segment, I accept it, here's what it looks like. If it had clipped it, you would get the clipped version here. So then here's the next line segment. It's accepted, here's what it looks like in the going to the next stage of the render. Since it's accepted without clipping, they look the same. So there's the second line segment. Then here's processing the third line segment. Here's processing the fourth line segment. We're still in that same color. Now we're going to process the fifth line segment. That's one of the ones on the top. Now see, they have the different color. See, now this color is going to get used over and over again. They're going to be using color index 1. So it's going to use color index 1 now. Okay. So now we're at the top edge, they're still using the same color indexes, but the line segment didn't have its color index changed. We just changed the object in the line in the color list. We updated the color object in the color list from the point of view of this picture here. When I randomly changed the color, I didn't change anything over here, didn't change anything over here. I changed what was in that list. By changing what was in that list, that updated the colors on all these guys. So they still were pointing to the same colors over here. Well, they're pointing to the same slots over here, but in those slots are different color objects now. So that's one way to change color, is to just leave all this stuff alone over here and just change what's in there. Okay? All right. Now, on the other hand, I may want to make these line segments, like if I do this, oops, let's see. Oh, let me turn off debugging. Oh, it's not responding. Something went wrong. Yeah, the render stopped responding. See, it's not refreshing the screen anymore. Okay, not sure what happened there. Didn't crash. Okay, let me restart it. Okay. Okay, now what if you set it to like here? I gave each edge its own color. That edge has a solid color. That edge has a different solid color. That edge has a different solid color. Now I have to do more than just change what's in here. I have to change what's in here, because now this line segment isn't going to share a color with that line segment anymore. Before, they were all the same color here, so these line segments all shared the same color. So now I had to reach in over here to these and do some changes there. So when I set the model to have every edge with its own color, so right now I'm randomly changing the colors of the edges, but each edge has a solid color. What I'm doing is I'm putting new color objects in here, but I also have to go through here and change what's in here so that each line segment, these two indices point to one color over here. Then these two indices will point to a different color over here. So by having these two indices point to the same color, I make that line segment a solid color, but I want it to be a different solid color than the other line segment. So now this line segment, it shares the same color at this end and that end, but it's a different color than that line segment. So now I've got a color for every line segment. So now the color list has to have 12 colors in it, one for each line segment, and then each line segment's going to use one of the colors. Okay, so when I use that was the if you use the help key, you see that the E key changed the random solid edge colors. Okay, so that was give each edge a solid color, but different than all the other edges. Whereas the capital E key changes the random edge colors in a rainbow kind of way. See, now each edge is kind of rainbow-like. That's the shift E key. See how this is shifting up? Some of them you don't see the shifting as well because the colors at the two ends kind of are close to each other. But you can see that the color is shifting across here. But the lowercase e key makes them a solid color. Each edge has a different solid color versus each edge having a different random color at each end. So this shifts from one color to another color. But notice that at this vertex here, this edge is coming in at one color, and this edge is coming in at a different color, and this edge is coming in at a different color. So at that vertex, there's three colors. One color for that edge coming in this way, one color for that edge coming in this way, and one color for that edge coming in this way. Okay. There's also, now here what I've done, there's one color at that vertex, and all three line segments emanate out from that color. But there's a different color at this vertex, but it's the same color for all three line segments. So this color, this edge is shifting from that color to that color. But at each vertex, it's the same color for all the line segments. And that, what that would do is, that one's a little bit more complicated. You have to figure out each line segment that's sharing a vertex and make the index in it point to the same color over here. So every line segment, like here, I have to find out that that vertex is shared by three line segments. So then I have to go in and say, okay, this line segment should have the same color at that vertex that this line segment has at that vertex, that this line segment has at that vertex. So I have to go through and figure out which line segments share a vertex, and then make sure that they all point to the same color at that end of the line segment with the shared vertex. So there's all these different ways you can color models, and this scheme gives us this versatility. And this scheme comes from OpenGL. This structure is the same structure that renders like OpenGL and DirectX use. It's called index attributes. The idea is that the line segment actually has two attributes: vertex and color. So it's got two sets of indices for each attribute. Later on, line segments will have a bunch of attributes. They'll have texture attributes, normal vector attributes, lighting attributes. So a line segment can end up, right now, at first we only had one attribute for a line segment, what its vertices were. So we didn't really point out that what was going on. But now we have a second attribute to each line segment. Notice that the color is not an attribute of the vertex, it's an attribute of the line segment. The line segment has two vertex attributes and two color attributes, okay? And then the attributes are actually indexes into color or vertex objects or vertex resources and color resources. So the line segment says, I'm going to use these two vertex resources, and I'm going to use these two color resources. And the GPU stores all the vertex resources in one place. It stores all the color resources in one place. It stores all the line segments in one place. And then the line segments are indexes into the resources. And that makes memory management a little bit better. All the vertices are in one place. So if you want to move the object, when you want to shift the object, all the vertices are in one place. So it's easy to shift them. So that gives you improved memory management. When it comes time to move this object, all the vertices need to be updated, so it's good that they're all in the same place. Otherwise, if the line segments held their own vertices, then you'd have some vertices in this line segment, some vertices in this, see, if the vertices were actually right there, if that was two vertex objects, and that was two vertex objects, then the vertices would be scattered all over memory. And then when you wanted to move something, you'd have to go hunt through memory to find that vertex, find that vertex, find that vertex. That would slow you down a lot. So the idea was put the vertices all in one place so that when it's time to move them all, they can all be moved together. But then the line segments need to point at them. Okay. Now for the color, it's not so much an efficiency. Having all the colors in one place, you don't shift the colors very often. So having all the colors in one place is just mimicking the way the vertices are. So the color attribute is just set up to mimic the vertex attribute. The vertex attribute's done this way for efficiency. The color is just done, well, if we're doing vertices that way, let's do colors the same way. Because it works well for vertices, so why not just do it the same way for colors? It works well. It doesn't speed things up in the case of colors, like it has significant speed up for vertices. Having all the vertices, if we had the colors here and the colors here, it wouldn't matter much. But if we had the vertices here and the vertices here, it would matter a lot when it came time to move things. Okay? All right, so that's the structure of this. Okay. Now, that's how the render stores these. The next question is, how does the render actually draw those? Like, how does the render actually get? Remember, what we're talking about is what's stored at these vertices. Yeah. So at that vertex is a color. Yeah. And there's one color at that vertex. Well, that line segment has points to one vertex and points to one color, and that line segment points to a vertex and points to a color. Okay, but then the render, when it renders that line segment, it looks up the vertex, it looks up the color, and then it uses them to draw it. Okay, yeah, it plots the vertex at the right point, but then it rasterizes the line segment. What we want to see now is that what the rasterizer does as it goes across the line segment is it interpolates using lerp from that color to that color. Okay, so that's the next little discussion. That's down here. Oh, the here's a discussion of the allocating line segments, vertex, color, and allocating line segments. So this is a discussion of the vertex list, color list, line segment list, how they're managed. So there's several examples given in here. Like, like here's an example of two line segments sharing a vertex. Okay, okay. The idea here is if you move that point, both line segments should drag with it. So I want the vertex I want the line segments to share that vertex and drag together. Okay, all right. So I would do that by saying, see, they share that same vertex. This line segment goes from 0 to 1, and this line segment goes from 1 to 2. So they share that vertex. But then what about the color? What if I want that line segment to be a solid color that's different than the solid color of this line segment? Okay. Or what if I want there to be a color here, then you shift to some color here, then you shift from that color down to there. So I want three colors, a color there, a color there, and a color there. And I want you to shift from that color to that color down to that color. Or I want one solid color all the way across. So what this thing talks about those different scenarios. What would you do if you wanted to have one solid color across here? What would you do if you wanted to have a color at that vertex, a color at that vertex, and a color at that vertex, and you shifted from that color to that color to that color? What if you wanted a solid color on that line segment and a different solid color on that line segment? Okay, so this shows you the way you would allocate, what you would put in the vertex list, what you'd put in the color list, and what you'd put in the line segment list to do those different kinds of allocations. Okay, so that's the discussion, what we were talking about. And that's what's going on over here. Actually, when I use these different keys over here to change the color in different ways, it became unresponsive again. I wonder what's going on. I've never seen it do that before. It's when I shift away from it, it's becoming unresponsive. Okay. Oh, no, no, I'm sorry, it wasn't unresponsive. It's too busy doing the debugging output to update itself. Yeah, see, the debugging output can be really useful, especially with small models. So I probably should make this, what this is the rasterizer. It's showing you all the pixels. Since this is a big screen, there's a lot of pixels there and a lot of pixels there. A lot of times, to make the renderer, the debugging output work better, one trick is to, before turning on debugging, make this screen real small. Because now there's not that many pixels. Okay. Now if I turn on debugging, there's not that much output. See, there's all the rasterization. See, the whole rasterization only took a second or two because there's not that many pixels. So if you want to like study what the render is doing, sometimes you need to make this window small over here. Now, let me turn off debugging, make the window big. Now every line segment's a heck of a lot of pixels. So there's just more and more pixels in every line segment. Now if I turn on debugging, see, it's going to take, that one wasn't too long. Okay. See, now it's taking a little bit longer. Okay, but see, the amount of time it takes for the debugging output's got to do with how big how many pixels there are over here. Okay, all right. Okay, so this discusses this idea of how to allocate things. Okay, now so here's the discussion of clipping. Then after clipping is rasterization. Here's the discussion of rasterization. And then here is anti-aliasing, and after see in the order so here's now color in the rasterizer. Okay, so here's the idea. Here's a line segment needs to be rasterized from this vertex with that color to this vertex with that color. So assume it's been clipped. So this is, you know, the discussions in the order of the pipeline. So after the clipping is the rasterizer. So now we want to rasterize from one vertex to another vertex using color. Okay. Now the rasterizer worked by just turning this equation, by writing the equation of this line and walking the equation of the line. You just walk the equation, you know, that's what's discussed over here. You just walk the equation of the line. Well, in this case, you're going to walk from here to here to here to here to here to here, and you look for the pixel with the nearest, the logical pixel that's nearest to the line. So you walk the logical pixels, and for each logical pixel, you go over and find, for each row of logical pixels, you find the logical pixel closest to the line. For that row, you find the logical pixel closest to the line. Well, there's the logical pixel closest to the line, and you turn on that whole thing. Now we want to say, well, what color do you give this pixel? 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 Okay, now this endpoint's got a color, and this endpoint's got a color. That's this color here and this color here. So the endpoints have color. So we know what color to put there and there. The question is what color to put as we go across here. Okay, and there's two ways to think about how to do that. Okay, you can take the equation of this line and write it as in a point slope form, or you could take the equation of the line and writing in the linear interpolation form. Okay, so that line can be written two ways, as y equals mx plus b, or in vector parametric way. Okay, either way, what we want to do is figure out how to interpolate color as we go across. As we shift across this line, how do we shift the color from this color to that color? And you could do it either using the y equals mx plus b equation of the line, or you could do it using the lerp equation of the line. Okay, if you use the y equals mx plus b equation of the line, you just find, like you take red there, and then write the equation from that red value to that red value using the slope of this line. That's this here. Use the slope of the line. I'm sorry. No, you compute the slope for the change in red. No, well, you compute a funny slope. You find the slope of the red component, change in red over change in x. How does the red component change as you change x? If I change x a little bit, how much did red change? If I change x a little bit, how much did red change? If I change x a little bit, changing x is run, changing red is the rise. Okay, so I'm finding the slope of the line in I'm finding its rate of, remember, slope is, calculus is called rate of change. I'm finding the rate of change of red. And here I'm finding the rate of change. This is the rate of change of green. How much does green change across the line? How much does the line? This is change in output over change in input. As I change input from here to here, go across the line. If I go across the line like that, how much did red change from here to here? How much did green change from here to here? And how much did blue change from here to here? So I get three equations. Okay, all right. And then if I plug in x values into those equations, I get red, green, and blue. So I plug in x values into these color equations, and I get red, green, and blue. So it's just using it's showing what y equals mx plus b is really there for, to create rates of change. I'm computing the derivative. This is literally the derivative r. This is the derivative of g. This is the derivative of b. Okay. So the slope of r, the slope of g, and the slope of b, and then say, okay, if you move this much in the x direction, this tells you how much the red changed. Add that change to the original red, and you get the new red. This is how fast green is changing. If you change x by that much, multiply it by the rate of change, that gives you how much green changes. Add that change to how much you started with, and that's the new green value. Okay, so you can do it this way. But you can also just lerp from the original. Now notice here, this is the red at left end, this is the red at right end, and this is the change in red. So I use the red at both ends to find the change in red. In the lerp formula, I say, here's the red at the left end, here's the red at the right end. I want to average them. So I want to put this much weight on the red from this end, and this much weight from the red at this end. And then as t changes, t represents how much, the time. See, at time 0, I'm here. At time 1, I'm here. At time a half, I'm in the middle. So I think, okay, at this time, I'm going to average the red at the left with the red at the right with these weights. And that'll give me a red in the middle. Okay, same with G. Here's the G at the beginning. Here's G at the end. If I'm at the 3/4 mark, so I'm 3/4 of the way between the left and the right end, 1/4 weight gets put on this, and 3/4 weight gets put on that. And I average the green and red. Notice that's a very different point of view. Rate of change of the color versus a weighted average of the colors. There are two ways of thinking about the same idea. And this duality between linear equations and lerp equations is, believe me, it's ubiquitous. If you study data science and statistics, you'll see this over and over again. People will freely switch between this way of thinking and this way of thinking all over the place. They're doing linear interpolation. Sometimes they do it with lines. Sometimes they do it with lerp. And they'll bounce back and forth between these because they're both doing the same thing. What's the color of red right there? Given that I know the red here and I know the red there, if I'm halfway between, what should the red be? If I'm 3/4 of the way, what should the red be? I'm interpolating between a starting value and an ending value. I can interpolate using y equals mx plus b, or I can interpolate using the lerp equation. They're really the same thing, just two ways of thinking about the same thing. I can think in terms of rates of change, or I can think in terms of weighted averages. Sometimes it's really advantageous to think in terms of rates of change. Sometimes it's really advantageous to think in terms of weighted averages. If you manipulate the algebra over here, you can get this equation out of it. By rewriting this a little bit, both of these can be gotten to either one by some algebra. They really are the same thing. Okay, so now the render that I wrote uses these. I wrote the renderer to use these, but the clipping algorithm uses these. The clipping, so the rasterizer, I'm sorry, I said the rasterizer uses these and the clipping uses these. And that's an example of how sometimes it's advantageous to think this way and sometimes it's advantageous to think this way. In the rasterizer, it was a lot easier to think this way. If we go over here's the rasterizer. You can go in and then you can find, if you look hard enough, you'll find the formulas that are doing the color interpolation. There's those. Okay. Well, actually, here's finding the slopes. So there is computing that slope. I need that slope, and that slope. So I pre-compute them. So there I compute the slopes. Okay. Okay. So I got the slopes computed because the slope's the same across the whole line. The slope doesn't change. Everywhere you go across this line, the slope is the same. So I can compute the slopes at the beginning. Okay. Then I'm going to have the loop that walks across the line. And then here is the formula computing the RGB using the slope. So see that now these three formulas are these three formulas with the slopes pre-computed. See, there's no reason to compute the slope over and over again. So you really wouldn't use that formula. You'd pre-compute the slope and then see, but there's that formula. And then there needs to be rounding because the, oh, actually, I'm sorry. The absolute value is weird. Why do I take the absolute value? There's a little comment here. Sometimes when the color turns out to be 0, this, because of I mentioned this, we saw this the other day. Floating point numbers are weird in languages. When this thing computes to 0, it sometimes comes out -0. But if you give -0 to the Java color class, it'll blow up on you. It'll throw an exception. The stupid Java color class does not like -0. When you create a color object, you give it a float, but it won't accept -0. So I had to take the absolute value of these numbers because sometimes they come out to 0. Sometimes the color at one endpoint is 0. But the floating point number algorithms can give you -0, but the Java color class does not like -0 color, so it throws an exception. So you have to take the absolute value of these guys. Okay. I don't know a way to stop these guys from returning -0s. Maybe there's some trick that I don't know about to keep these from returning -0s, but they quite often do give you -0s. -0 doesn't have any meaning in math, but it does in floating point number system. -0, there's two zeros, -0 and +0. Okay, and the Java color class, I think it's kind of, I don't know if it's a good idea or not, but the Java color class won't accept the -0 for color. Okay, so I had to put little absolute values in here. I had to wrap all these formulas in an absolute value to not get the color, because eventually we're going to have to create a color object out of these RGBs. I didn't want the color class to complain. Okay, all right. So the rasterizer uses these formulas. Okay, now the clipping algorithm needs to do something similar. Okay, so here is color in the clipping algorithm. So here's the idea. We're going to clip this line. The line has a color at one end and a color at the other end, and we need to clip it there. And what we need to do now is we need to find a new color for here. See, remember, this line is going to get clipped. It's not being rasterized, it's being clipped. And we're going to put a new vertex there. When we create a new vertex there, we have to figure out what color should go to that vertex. If we just copy that color to there, it's not going to really be the right thing, because that line, if this is red and this is blue, this is purple here. Because you would interpolate from red to blue, in the middle would be purple. So you can't just copy blue to there. You have to do the interpolation when you do the clip. Okay. Now the clipping algorithm is already using lerp, so it turns out that if we lerp the colors at the time we lerp the vertices, it works out real well. Okay, so that's just pointed out right here that the clipping algorithm is already, here's the explanation of the clipping algorithm. It's using lerp to find that point there. Okay, so it's using the lerp formula. So then all you have to do is say, well, once you've got the t from the lerp formula that's going to lerp between that vertex and that vertex, just use that t 3 more times to lerp between R, G, and B. Okay, so there's not much to say. Just since you're lerping the vertices, just go ahead and lerp their colors with the same t value. And then if you look up the clipping algorithm, down here's where the actual clipping happens. Okay, here's the calculate. Here's when we talked about this the other day. Here's the calculation of the t, of the lerp, the value t. And there's 8 cases, because you could have x not being on the wrong side of that line, or you could have x1 being on the wrong side of that line, or you could have x not being on the wrong side of that line, You could have x1 being on the wrong side or x1 being on the wrong side of that line. So there's 4 lines to clip on. There's 4 lines to clip on. There's 4 lines to clip on, and then each clipping line could have either V1 on the wrong side of it or V0 on the wrong side of it. You could have either V1 or V0 on the wrong side. So that gives you 8 possible cases. And I can't figure out any way to make these 8 cases somehow more efficient. The only way I can do it is to just do 8 cases. Case 1, case 2. Okay, so there's the computing the T in 8 cases. Okay, once you've got the T, there you use lerp to find the new X and Y, and there's lerp to find the new RGBs. Okay, right? The only thing I have to do is cast T to a float, because the RGBs are floats, not doubles. So we're using doubles for X, Y, and Z, but we're using floats for R, G, and B. And we're using floats for R, G, and B because that's what Java decided. The Java color class wants floats in its color objects, not doubles. I don't know, I'm not really sure why, but they chose to put floats in the color class, not double. So the points are X, Y, and Z are double, but the colors are floats. So I cast T to be a double. I call it T underscore, and then use the lerp formula 3 more times to lerp between the 3 colors. Okay, so do I have a question?
I was just going to say, could it be because of memory? Because if there's all those pixels on the screen or doubles, and it takes up way too much memory.
Yeah, and Java was invented 25 years ago, and it very well might have been back then. Yeah, they may have been more worried about memory. Now memory's dirt cheap.
Right.
Yeah, almost nobody worries about memory anymore. But 25 years ago, that every color, instead of being, that halves the amount of space. And now, why would you want to use doubles? Like, why do I want the vertices to be doubles? What do the doubles give me that are better than floats? They take up more space, but
better precision?
Yeah, I get more precision. Well, do I want more precision with colors?
Not really necessary, I don't think.
Why not?
Because there's only
the human eye, yeah, there's only so many colors the human eye can see.
Yeah, there you go.
Yeah, the extra precision that doubles give you is useless for colors because the human eye can't see that many colors. Okay, now why would you want to use doubles? Because almost everyone writes their code using doubles, and so switching between doubles and floats is a nuisance. But you don't gain any, like with these vertices, I do gain precision by using doubles. Okay, but with the colors, I don't gain. Using doubles for colors is not really all that useful. So Java chose floats because I think, yeah, because they're half the size. Okay, so use lerp for colors in the clipper, but use linear equations for color in the rasterizer. Okay, so now either one can use either one because they're completely equivalent. Lerping and linear equations are really just 2 ways of saying the same thing. Linear equations, y equals mx plus b, or lerp, vector parametric equation of a line. It's just sometimes this is better, sometimes this is better. Sometimes you want to switch from between them. The rasterizer was already using linear equations, so the rasterizer did the color interpolation using linear equations. The clipper already was using lerp for lerping the vertices, so might as well have the rasterizer use lerp for the colors. Okay, all right. So there's 3 issues with. So let me just say, the last thing to point out is we've talked about 3 things. When you add colors to the render, you have to worry about how do you store colors. That's the allocation issue. How do you store colors? Then how do you use color in the rasterizer? And how do you use color in the clipper? So the README for render 5 just covers those 3 things. So the README says How do you store colors? How do you use them in the rasterizer? How do you use them in the clipper? But the overview, since the overview is trying to describe the whole renderer, those facts are spread out in this whole document. So it covers the whole renderer from beginning to end, and it talks about, here's where it talks about color management. So it talks about that here first, when it's talking about the structure of the scene graph. Okay, and then when it gets to like projection, has nothing to do with color. Okay, then here's the clipping discussion. So there it talks about the clipping, and then it talks about color in the clipper. Okay, so that's when color is brought in. Okay, and then it talks about some more stuff about clipping. Then it gets to rasterization. Okay, this is all the same stuff about rasterization, but then at the end it says, well, we have to talk about how the color is interpolated in the rasterizer. So here, the new information is just folded in to the whole document. If you just want to know exactly what each renderer does, the README tells you what's added new in that render. Okay, so we run out of time. Okay, so now our renderers can do fancy colors. Okay, the real issue is that we're adding attributes to vertices, to line segments, and we're going to see as we go on, we're going to add more and more attributes. Every line segment will have vertex and color, and then it'll have a normal vector and lighting properties, and it will end up in texture coordinates. So every line segment will end up with having a whole bunch of attributes. Okay, so we'll get closer and closer to what OpenGL lets you do. Okay, so we've run out of time. So if you have questions about the homework assignment or the review problems, let me know. And anybody have any question right now? Does anybody have a question?
Yeah, whenever you're done with everyone, I would like to show you a bug that I have.
Okay, well, we'll do that in a separate meeting. I think that'll
Yes,
work better. So I'll shut this one down, and then we'll start another one up, okay?
Okay, should I Zoom you or you Zoom
Yeah,
me?
you Zoom me. That'll be, yeah, please Zoom me. Because I'll
All
be,
right.
right, as soon as it's over, I got to upload the video and do some other things. Okay?
All right. Should
Anybody,
I wait like a half hour or something?
no, just wait a few minutes.
Okay.
Okay. Anybody else, any other question about, any question about the homework? Any outstanding question about the homework that's important? Okay.
I did have a question, not about the homework. It was about an email that I sent you. I'm looking for a professor to sign up with for senior design.
Okay. Yeah, the senior design it's gotten kind of messed up because there's too many students, and we have to figure out how to allocate them. So we're trying to work on that. My wife got sick, and I've been having a hard time keeping up with emails.
I understand.
Yeah, my wife got sick. Professor Elias got sick, and right now I'm really pressed for time. So I'll try to get to the emails I'll try to get to the emails as soon as I can. So, and also we have a problem with the senior design. There's we have to figure out how to allocate students.
Is there a good resource or someone to talk to about possibly getting put on a waiting list almost? Or
no, there's not that many students, so we don't need a waiting list. No, we just have to figure out who can do which students, because like I've had like 8 or 10 students ask me for senior designs, and there's no way in the world that I can do eight or so. So have to find a way to balance things out.
Okay. Do you know which other professors will be doing senior design?
Yeah, well, Professor Zhang and Professor Yang will be, because Professor Zhao is on sabbatical. She's got to leave she's not going to be teaching next semester. She has a sabbatical. So there's 3 of us.
Okay.
Yeah. So the 3 of us, Professor Zhao isn't doing any because she's going to be on sabbatical.
Okay.
Okay. So I don't even know how many students need, like one thing I've been asked and I haven't got an answer to yet is how many students need a senior design this semester. So I'm not even sure what the number is. Like I haven't seen that number yet. I'm trying to find out what that number is. Okay. So if send emails, but and if you don't get an answer, send another one and remind me. But I've been kind of slow in answering them because I've been really pressed for time lately. Okay. Anything else? Okay. Let me go ahead and stop the sharing and have a nice Halloween. This is Halloween weekend. Have a nice Halloween and see you on next Tuesday. Bye.
But
We'll see.